DSSC3 dye-sensitized solar cells. Hello and welcome to D Creations Resources. We have been talking about DSSCs, and the working electrodes in DSSCs are prepared by depositing a thin layer of oxide semiconducting materials like TiO2, Nb2O5, ZnO, SnO2, etc. on a transparent conducting glass plate which is made of FTO or ITO. Now, the band gap of these oxides, these are basically wide energy band gap oxides, so the band gap is around 3 to 3.2 eV. Now, even in case of different crystal forms of TiO2, we have already spoken about crystal forms of TiO2 in the previous episode. So here Anatase allotropic form of TiO2 is more preferred because it has higher energy band gap, 3.2 eV, and the band gap for rutile TiO2 is around 3 eV. Of course, there are oxides which have similar band gaps, but TiO2 is preferred because it's non-toxic and less expensive and also easily available. So it's mostly used as a semiconducting layer. Now these semiconducting layers are able to absorb only a small fraction of light in the UV region. So what is done? These working electrodes are then immersed in a mixture of a photosensitive molecular sensitizer and a solvent. So after soaking the film within the dye solution, the dye gets covalently bonded to the TiO2 surface. Due to the highly porous structure and the large surface area of the electrode, of course, high number of dye molecules will get attached on the nanocrystalline TiO2 surface. And so the light absorption at the semiconductor surface increases. So here it talks about different aspects. It talks about the importance of TiO2. It also tells you why a nanocrystalline electrode is preferred. Because as you know, in case of nanomaterials, the surface area is dominant. The surface area to volume ratio is also very high. And of course, as the structure is porous, there is going to be larger surface area for the dye molecules to get attached to. And so the light absorption at the semiconductor surface is going to increase. And that is very important, having more light, because we know how efficiency is related to the incident number of photons. Now to talk about the photosensitizer or dye. Dye is basically the component of DSSC which is responsible for the maximum absorption of the incident light. So in order to do that, what properties should it have? First of all, it has to be luminescent. Secondly, the absorption spectra of the dye should cover ultraviolet and up to near infrared region, so UV visible NIR region. Now it is preferred if the periphery of the dye is hydrophobic to enhance the long-term stability of cells, because it results in minimized direct contact between electrolyte and anode, and otherwise water-induced distortion of the dye from the TiO2 surface can appear, and if that appears, of course the stability of the cells is going to reduce. Also, in order to avoid the aggregation of the dye over the TiO2 surface, some co-absorbents are used like carboxylic acid groups or phosphoric acid, etc., and they are inserted between the dye and TiO2. So this results in the prevention of dye aggregation and thus limits the recombination reaction between redox electrolyte and electrons in the TiO2 nano layer, and there are stable linkages which are formed. So we know that here recombination needs to be avoided if you want high efficiency. Now what about the electrolyte? What properties should it have? Well, the redox couple in it should be able to regenerate the oxidized dye efficiently. It should have long-term chemical, thermal and electrochemical stability, of course. It should be non-corrosive with the DSSC components, and it should be able to permit fast diffusion of charge carriers, enhance conductivity and create effective contact between the working and counter electrodes. Also, the absorption spectra of an electrolyte should not overlap with the absorption spectra of a dye for the obvious reasons. So which are preferred electrolytes? I minus or I3 minus based on iodine are preferred, and they are highly efficient electrolytes. Of course, ionic liquids have their own drawbacks, and in order to avoid that, even solid state electrolytes are developed. Now, another important parameter or another important part of DSSC is the counter electrode. They are usually prepared using platinum or carbon, and both working and counter electrodes are sealed together, and subsequently an electrolyte is filled with the help of a syringe. And counter electrode catalyzes the reduction of, say, I minus or I3 minus liquid electrolyte and collects holes from the hole transport materials. So platinum is used as a counter electrode because it demonstrates higher efficiencies, but it's very costly and it's less abundant. So some alternatives are being developed in order to replace platinum, and carbon can be used, or there could be some alloys like iron, selenium, FeSc, etc. Now, what is the working principle? So the working principle is going to involve 4 basic steps. Number 1, light absorption. Number 2, electron injection. Number 3, transportation of carrier. And number 4, collection of current. So to describe it, first the incident light or photon is absorbed by the photosensitizer, and thus due to photon absorption, electrons get promoted from the ground state to the excited state of the die, where the absorption for most of the die is in the range of 700 nanometer, which corresponds to the photon energy of around 1.72 electron volt. Secondly, now the excited electrons with a lifetime of nanosecond range are injected into the conduction band of nanoporous TiO2 electrode, which is basically lying between, or rather lying below the excited state of the die, where the TiO2 absorbs a small fraction of the solar photons from the ultraviolet region, and so the die gets oxidized. Now these injected electrons are transported between TiO2 nanoparticles and diffused towards the back contact. What is the back contact? It's the TCO, transparent conducting oxide. Through the external circuit, electrons reach at the counter electrode. Now the electrons at the counter electrode reduce I3 minus to I minus. Thus the die regeneration or the regeneration of the ground state of the die takes place due to the acceptance of electrons from I minus ion redox mediator, and I minus gets oxidized to I3 minus. And then the oxidized mediator I3 minus diffuses towards the counter electrode and reduces to iodine ion. So these are some of the important steps in the working. Now, of course, the performance of DSSC is evaluated by plotting a IV curve, and it will consist of short circuit current, open circuit voltage, maximum power output, overall efficiency, fill factor, etc. Now, what are the limitations? What are the limitations of these devices or DSSCs? So there are limitations pertaining to stability. So limitation towards extrinsic stability and intrinsic stability. Also, a huge amount of loss in energy of oxidized die takes place during the process of regeneration due to the energy mismatch between the oxidized die and an electrolyte. Now, of course, a lot of research is being carried out in order to reduce these limitations.